Okay, so let's start with the first classification method that we're going to see in this class and in this course, as a matter of fact, and it's going to be logistic regression. The fact that you see regression in the name, in fact, means that it's going to be highly related to the regressions that we already saw in class number 4. So let me explain you a little bit how. If you look into the points that we have here, the data points that we have here, the crosses and the circles, or the X's and the circles, you could think of different types of classifiers or regression, right? Imagine that we have those points. If you think of a line that could represent a linear regression, that could represent those points, it's going to be hard, right? Because the points are basically just either 1 or 0. Okay, a line that represents that is going to always have an error. Okay, so maybe what this is telling us is that regression is not the solution, that we should be looking more into classification, right? Can we classify this as being, above 0.5 or below 0.5 and define two different classes? That could be a perfect classifier, right? So logistic regression goes into that direction, okay? So basically, what happens when we have a problem like this one, which we want to solve with a regression approximation, but we have a binary output. Okay, we know that we have two classes, and we want to define a model that reduces the prediction errors, and we know that probably the best way to do that is just by taking into account that it's a binary output, but with a model definition very similar to what a linear regression is. And this is where logistic regressions come in, right? So logistic regressions are based on the logistic function, which has the definition that you see there, basically based on an exponential function exponentiated to a negative c value. And what this logistic function does is that it squeezes all the input values into values between 0 and 1. Okay, so basically for any input that we have, that value is going to be squeezed into 0 and 1. And so by squeezing the value between 0 and 1, it's much easier to define a binary classifier that will determine whether that given input sample is of one class or of another one. If you look at this expression here, okay, if you look at there are a couple of important observations here. The first one, the probability of y equals 1, given x, what's the probability of y equals 1, or given x, what's the probability of y equals 0? What this is telling us is that the logistic regression is in fact a model that is based on probabilities, in the sense that being from one class or another one is going to be based on the probability that that label can happen based on the input features that we have. Okay, so given a set of input features x, what's the probability that the label associated to those features is 1 or is 0? Okay, that's what we are trying to model here. And that's going to be our classifier. And of course, the label that will be given at the end of this process is going to be the label associated to the highest probability. So if the probability of given x, y equals 1 is higher than the probability of y equaling 0, then the final label given to that input x is going to be 1, and the opposite. Okay? So because of the way we have defined the function to squeeze the values between 0 and 1, basically what you see there is squeezing the values from a linear regression between 0 and 1 values. This is exactly what that means. Okay, if you take a look at the denominator, okay, of this quotient here, and if you see the exponent of the exponential function, you will see that's probably very familiar to you, right? I mean, that's that beta 0 minus beta 1 x1 minus beta n xn. It's exactly representing a linear regression on the input features x. Okay, and that's precisely that. So what we are doing is, given a set of input features that we could in fact regress as part of a linear regression and extract the final value, what we are doing is basically that final value, we are squeezing it between 0 and 1, and we are computing, what's the probability of that event happening. Okay? And the second quotient is exactly the same one, okay? But in this case, because we are the probability of given x, y being equal to 0, which is, and y is, the other label that the sample x can get, it's basically 1 minus the probability of given x, what's the probability of y being equal to 1, okay? And 1 minus the formula above is exactly the one that you see here, okay? So where all the beta values, the negative, instead of being negative, they are positive. It's just the result of doing 1 minus the probability of y equals 1 given that x is happening. Okay, it's just, if you do the numbers, this is the formula that you will get. Okay, so exactly the same thing that happened in a linear regression happens in a logistic regression, right? I mean, so how does this work? Again, as I mentioned in the linear regressions, when we saw the linear regressions, what we are seeing here is how the model is computed. Okay, what we are seeing here is, okay, how can I build a black box that given a set of features will tell me whether the label is 0 or 1 using logistic regression, okay? We are seeing exactly what happens in that black box. Then we will also see how to use the black box in R, okay? But it's very, very important that you learn what's going on within that black box, because otherwise, you will just randomly applying different techniques to data without exactly knowing whether that's even possible, okay? So it's really important that you understand how these different models are being built. So again, similarly to linear regressions, for the case of logistic regressions, if you take a look at the formulas here, the only thing that we need to learn in order to compute the model itself are the beta values, right? The beta values, or the weights, however you want to call them. And basically the role that the weights play is if basically they try to separate the samples, the positive samples from the negative samples, right? So what the weights are going to do is that they are going to be large for one type of samples, in this case for the positive training samples, okay? And the value should be small for the negative training samples. Why? Because again, we are trying to build a classifier, okay? And this type of classifier is, as we said before, is discriminative. So what we're looking for is, okay, what's, the line that's going to separate one from the others. So we learn the weights exactly the same way that we learned the weights for the linear regressions. Okay, remember that we defined the value of risk or loss, exactly what's the difference between the actual output from the classifier with respect to the label that we have in our training set. So basically we use exactly that same measure to understand or to model the weights. Okay, so we take the training data and part of the training data is used to cross-validate the model. So basically, what are the weights that will minimize that risk of loss, that will minimize that risk or loss, so that will minimize the difference between the actual output and the output that we are looking for. And in this case, because we are talking about logistic regression, we are going to define logistic loss. Okay, but it's exactly the same thing. So the formula that you see there, okay, it's basically capturing or defining the logistic loss. And what we are doing there is that we are defining, okay, what's the probability that given the set of weights that we are currently considering, given that set of weights, what's the probability that given a set of input independent variables x, the final label will be y. Okay, and that should be defined for every single different label that we have in our training data. So if we are looking into a binary problem, okay, then y to the I would be either one value or the opposite, because it's just a binary problem. Okay? So what you see in the second line of the formula is exactly that. Okay, so we are looking into, because we only have two classes, the log likelihood of y taking value 0 or y taking value 1 is reflected by these two log likelihoods that you have there. Okay? And again, what this is doing is simply a way of saying these are the errors that we want to minimize, okay? And basically, this is the function that we are going to use to obtain the best parameters that represent the best model and then minimize the error. Okay, is that clear? So again, the L is representing the loss function. We want to minimize the difference between the actual and the real values. The way we do this is with the log likelihood function, which is that log P that you see there. And the formula on the second line, what that formula is representing is basically, what's the log probability for each of the two possible cases that we have. What we don't know there are the weights, and those are the ones that basically we want to compute. So what we do is that we try to maximize or minimize the loss error by maximizing the log likelihood. Okay, and we do this by using the maximum likelihood estimation, the MLE algorithm that we already explained for linear regression. So for the maximum likelihood estimate, basically what we are doing here is that we are looking for the maximum, okay, L value. And again, we try to minimize the loss, but we try to maximize the log likelihood that that will happen. Okay, that's the reason why it might seem counterintuitive, but you are minimizing the loss to get the best model, okay, and that best model is associated to the maximum log likelihood. And so basically we're just finding or looking for the maximum for that loss, okay, which is just finding the maximum weights in the loss formula that we have defined. What happens in this case is that similarly to other cases that we've seen, this has not a closed form solution, so we cannot solve it mathematically to the optimal solution. So what we do is that we use gradient descent, and we try to find basically by derivating this and equaling the derivative to 0, we can extract what are the weights that could give us the best possible value. We're not going to do that, okay, but just keep in mind that that's the way this model works. Okay, so when you are trying to, or when in R, you will create your own logistic regression model, exactly what this entails is that internally the model is taking the training data and is trying to understand, with a cross-validation sub-data set, is trying to understand what are the best weights, and finding those best weights is just a matter of maximizing the log likelihood that any of the two potential labels might happen given the input and given a set of weights. Okay, once these weights are found, basically the model is trained, and once the model is trained, it can be used to test or to predict whatever we want to predict. In this case, it will be in a binary setting. Okay,